We haven't discussed the definition of solution in a while. This is something that's important. You got to know what that means. If you want to know if something is a solution, it makes an equation true. It satisfies the equation, okay? So they've got ordered pairs here. These ordered pairs represent points, right? We could graph that. We could graph that. We could graph that. We could graph that. And we have this equation, and this happens to be what kind of equation? This is a linear equation. So we want to know if these ordered pairs make this linear equation true. What we're really asking is the point on this line. If it is a solution, if it makes it true, that means that point is on that line. So here's what you do. As long as you get your x and y in the right spot, you're probably going to be okay. So x is 2, y is 3. So we're going to take y equals 5x minus 7. We're going to substitute 3 for y. 5 times 2 for x. Then we're going to do a little bit of work here. 10 minus 7, does that equal 3? It does. So that means this point is on the line. It is a solution. If we were to graph this line, and we all know how to graph this line, the point 2, 3 is actually on this line. Okay? Now, what about 0, 6? Let the 0 be x, the negative 6 be y, because it's an ordered pair. So we're asking, is negative 6 equal to 5 times x is 0 minus 7? So we get what? Negative 6 equals 0 minus 7. Does negative 6 equal negative 7? No. So this point is not on this line. If we were to graph this line, 0, negative 6 is not on this line. Okay? So you pause the video. I want you to try these two down here. Find if they're solutions. Find if they are on the line. Okay, I found that the point 414 was not a solution. That means this point is not on this line. And I found that negative 3, negative 22 is a solution. It is on this line. And this is something you need to keep in mind anytime you're asked if something's a solution. Plug it in and see if it makes it true. The next thing we need to go over is how to decide if something is linear or nonlinear. We have talked about linear many, many times over the last few weeks. Linear means the graph is a line, right? Nonlinear means it's not a line. So if you're given a graph, this is going to be very, very simple. I look at this. Is this a line? Yes. So this one is linear. I look at this graph. That is not a line. So I would say this one is nonlinear. So how do we tell from a table if a relation is linear? Well, we could graph it, but graphing is usually a pain. So we're going to look at the slope. We have said that for something to be linear, it's got to have a constant rate of change. That means that the slope has to stay the same all the way throughout the relationship, okay? So that means we have to find our delta y's and our delta x's. So here, from 10 to 30 is plus 20. From 30 to 50 is plus 20. From 50 to 70 is plus 20. 1 to 3, plus 2. 3 to 5, plus 2. 5 to 7, plus 2. So my change in y over my change in x is 20 over 2, which is 10. And this is actually a average rate of change, right? So this is $10 per hour. So this one is linear because it has a constant rate of change. The rate of change stayed the same all the way throughout the relationship. Now, this next one, we have students and the number of magazines sold. So we're going to find our change in Y and our change in X. So 100 to 110 is plus 10. 110 to 200 is plus 90. And 200 to 240 is plus 40. Now, this looks suspicious, but let's check our change in X. 10 to 15 is plus 5. 15 to 20 is plus 5. 20 to 25 is plus 5. So when I check my change in Y to change in X, I get 10 over 5, 90 over 5, and 40 over 5. Are those the same thing? No, they are not equal. So this is nonlinear because there's not a constant rate of change. Okay? Now, let's look at the next one. We've got days and dollars. So let's see. 15 to 20 is plus 5. 20 to 30, plus 10. 30 to 40, plus 10. 40 to 55, plus 15. 55 to 65, plus 10. Now, just because these are different, you cannot say this is nonlinear. You have to check your change in X's. So I have plus 1, plus 2, plus 2, plus 3, plus 2. Now, check all your change in Y's over your change in X's. I've got 5 over 1, 10 over 2, another 10 over 2, 15 over 3, and another 10 over 2. Are those all the same thing? Yes, those are all equal to 5. So this is linear because there's a constant rate of change. Remember when we drew triangles on the graph and we drew little triangles and big triangles and they all simplified to the same thing? We drew similar triangles. These would be similar triangles. 5 over 1 would be a little triangle. 15 over 3 would be a bigger triangle, but they both simplify down to 5. All right, so we've looked at graphs. Those are easy. We've looked at tables. Not too bad. We've found rate of change from a table many times. Now we're going to look at equations, okay? So the first thing I want you to do, we have used Desmos before. When I finish giving instructions here, I want you to pause the video. I want you to go into Desmos, and I want you to graph these equations in Desmos. So you're going to type these equations in. You're going to see if you get a line or not a line. So you're going to write linear or nonlinear in the blanks. If you need help typing anything into Desmos, call me over and I'll help you. But actually type these into Desmos, look at the graph, and tell me if these equations give you something that's linear or nonlinear. All right, what'd you find? Now, these two should not have surprised you, right? Those are both in slope-intercept form. Everybody knows how to graph these two equations right now as is. These two look different, so that should have been a clue that something was up, and should have all had a different sort of shape. A cubic graph does that sort of S deal. 2 over x might have given you two little u's, something like that. A squared x gives you a parabola. Okay, you learned about those in algebra. So look at what gave you linear and what gave you nonlinear. I want you right now to pause the video again, and I want you to write what you think makes an equation nonlinear. Just write a couple of things that you notice and what you would look for to see if an equation was linear or nonlinear. All right, here are two things I noticed. Now, these are not the only things that make an equation nonlinear, but this is what I noticed. The variables can't have exponents other than 1. Now if there's not an exponent, remember you learned a while back, there's a 1 here. So this is x to the first, this is x to the first. But when it was x squared or x cubed, that gave you a non-linear graph. So if the variable is anything other than 1, if the exponent, of the variable is anything other than 1, it's nonlinear. This one looked a little weird because the x was in the denominator. So you can't have any variables in the denominator. Basically, if it looks like what we've done in class, normal y, normal x, they're separated, no funny exponents, no funny fractions, then it's linear. If it's in slope-intercept form, it's linear. If it's got an exponent or the variable in the denominator, it's nonlinear.